Alright, in this video we're going to review horizontal circles and we're going to go over vertical circles with gravity. So a horizontal circle, we're going to have it rotating counterclockwise to the left, and at any given point on this circle there will be a force directed toward the center that is centripetal. So let's assume for this particular example that we're spinning a mass on a string. And therefore the centripetal force will be tension. So when we draw our free body diagram, the only force acting on the object is tension toward the center. The net force will be mass times the centripetal acceleration, and the net force will be tension, and therefore tension will equal mv squared over r. So the whole point of this is to recognize that there's one force acting on the object. It is the only centripetal force. Centripetal force is a net force, so in this case the net force is only tension, and it will equal mass times centripetal acceleration, where centripetal acceleration is v squared over r. Well, if we look at a second example where we have a car on a track, I believe we did this one in class, we're going to have velocity tangent to the circle, and therefore one force acting on the object, and that force will be friction. So when we draw a free body diagram on this one, though, we have weight and we have normal force, where normal force will equal its weight, and the friction will be directed toward the center, and the friction will be the centripetal force. So this is a car on the track. The mg will cancel out basically because they equal each other. The net force will be mass times acceleration, and the net force will be friction, where friction is going to be equal to mv squared over r, substituting v squared over r for the centripetal acceleration. And then we get to substitute in the equation for friction, which is mu, the coefficient of friction, times the normal force. And it will equal mv squared over r. And then we recognize that normal force is also equal to weight, and so therefore it will be mu mg equals mv squared over r. And that's kind of a review of what we've done in horizontal circles in class. So now we're going to talk about vertical circles with weight. So now with vertical circles with weight, at any given point, the weight will always be toward the center of the earth. So in this case, our earth is down, so weight will be down. And we assume there is a constant speed for this object. So that means the velocity is not necessarily constant. The reason velocity is not necessarily constant is because it may have a constant magnitude, but it is changing direction, so velocity is not constant. So we're always going to have weight down here, and then while we're doing this spinning a mass on a string, what we are going to get is that it will travel with a constant speed around the circle, but it will be accelerating toward the center. So just because it has a constant magnitude of velocity does not mean that the acceleration is zero. The magnitude may be constant, but its direction is constantly changing. So we're spinning a mass on a string, and so what we have is two forces acting on the object. There will be tension down and weight down at the top. So this will be at the top of the circle. At the top of the circle, if we are accelerating, the acceleration will be toward the center because we have a centripetal acceleration. So at the top of the circle, it will be looking like it's going down. Tension will be down and weight will be down. So we will do the exact same thing where we write our net force equations. One of them is going to be mass times centripetal acceleration. The other will be tension plus weight here. And therefore tension plus weight will equal mass times centripetal acceleration. Now knowing that centripetal acceleration equals v squared over r, we can substitute in v squared over r for the centripetal acceleration. And therefore tension plus weight will equal mv squared over r, just like we did earlier. But this time we have to recognize that the centripetal force is actually a centripetal force is. There are two forces causing the acceleration toward the center. But we have to talk about what would happen if we were to try to keep this object in a circle at a minimum speed. So if it's at a minimum speed, the slowest we could possibly spin this mass to keep it in a circle, we would have to do that at a point where the tension would equal zero. So if that was the case, the tension would cancel out and the masses would cancel out, and we would have our centripetal acceleration would equal gravity. Now how we can do that is if you were to spin it in a vertical circle, a mass on a string, and that string was to reach the top and there wasn't enough force to keep it, the string tight, it would fall and fall all the way down and be at the bottom of the circle. We wouldn't even have a circle anymore. But if we were to keep it at a minimum possible tension where it could be straight string and stay at the top, at that point the tension would be zero and weight would be the only thing acting and holding it toward the center and keeping that string tight. So therefore gravity would be equal to the centripetal acceleration. So at the bottom of the circle, we're going to have weight down but tension up. Therefore tension equals mg is what most people want to do, and that is not true. And the reason it's not true is because we are accelerating. In this case, where our acceleration is taking us toward the center of the circle, and that is up in this case. So usually when we draw a free body diagram like this, we set tension equal to mg, call it a day, and move on. But since we're in a circle and it's accelerating toward the center, there's a centripetal acceleration, we cannot do that. In this case, tension would be greater than weight. So let's write our net force equation where net force equals mass times centripetal acceleration, and therefore it will equal tension minus weight. So we have net force equals tension minus weight, and then we can do tension minus weight equals mass times acceleration by setting them equal to each other. And then we substitute v squared over r in for the centripetal acceleration. There are two things that are occurring here with tension. The first one is that tension is going to beat weight. It's going to win in this situation. It's going to accelerate the object toward the center of the circle. The other thing that is going on is that it is providing centripetal acceleration. It is providing a force toward the center that is the centripetal acceleration. But it is being countered with weight down, so we have to include that. Since centripetal force is a net force, we have to include all the forces acting on the object. So in this case, the tension is the centripetal force that is causing the force to be accelerating toward the center. So the equations we have written here, tension minus weight equals mv squared over r, and tension plus weight equals mv squared over r, the two ways we're going to find net force for things at the top and the bottom. We will figure out how to do things at the side of the circle at a later date, and we'll do a lot of practice with these problems in class.